In this lecture, I am going to show to you how to derive the mean, the variance, and the moment-generating function for a binomial distribution. Binomial distribution is a discrete distribution with its probability mass function shown here. Probability of x equals to x given the parameters n and p is equal to n chooses x times p raised to x times 1 minus p raised to n minus x. The domain x has values from 0 until n, and p has a value from 0 to 1. So before starting our derivation, I want you to recall something, that the summation of the probability mass function from x equals to its lower bound until the upper bound is equal to 1. This is a property of a probability distribution, aside that the probability mass function should be always greater than 0. So in here, the sum of the probabilities is equal to 1 from the lower bound up to upper bound of our domain x. So let's start. We will use this fact for our derivation of mean and variance. So let's start with the mean. Mean, this is equal to expectation of x is equal to summation of x times the probability mass function, which is here, and chooses x, times p raised to x times 1 minus p raised to n minus x from our lower bound x equals 0 until x equals to n. Please take note that if x equals 0, this is 0, then this whole term is equal to 0. Then what we're left with is from x equals 1 until n. So we can just change it to 1. To evaluate it, I want to transform this x times n chooses x. So I will rewrite here x times n chooses x. This is equal to x times the combinatorial formula n factorial over n minus x factorial times x factorial. Please take note that I will use this one as scratch paper. N factorial. This is equal to n times n minus 1 times n minus 2, etc. until 1. I can take this one can become n minus 1 factorial. So n factorial is equal to n times n minus 1 factorial. So I will use this fact for n and x. So I can have x times n minus 1 factorial over n minus x factorial times x minus 1 factorial. I can cancel out x because same here. So I'm left with n times n minus 1 factorial over n minus x factorial times x minus 1 factorial. So for the n minus x, I want you to take note that n minus 1 minus x minus 1, this is equal to n minus x because negative 1 plus 1 equals 0. So this one can become n minus 1 minus x minus 1. So this term here is equal to n times n minus 1 chooses x minus 1. Now we can now evaluate our mean. So our mean, this is the summation, is equal to summation of I want to use this x times n chooses x, and this substitute it here. Substitute this one into that x times n chooses x. So this is n times n minus 1 chooses x minus 1. And I want to divide this p raised to x. I can have p raised to x minus 1 times p, because x minus 1 plus 1 is equal to x, which is x here. Then I will retain this 1 minus p and raised to n minus x. Now I can move out n and p because they are not dependent with x. So this is x anyway, this is x equals to 1 until n. So this one is equal to n times p times summation of n minus 1 chooses x minus 1 times p raised to x minus 1 and 1 minus p raised to n minus x. I want to prove that, let this one is x equals 1 until n. I want to prove that this term, this summation is equal to 1 by transforming the variables into another variables. So let this x minus 1 equals to y and n minus 1 is equal to m. So I will get this one. Let's rewrite it here. np times summation of, so n minus 1 we have m, and x minus 1 we have y, then p raised to x minus 1 we have y, and 1 minus p. So what is n minus x? So n minus x, this is n equals to m plus 1, so we have m plus 1. So n minus x is equal to m plus 1 minus, what is the value of x? This is y plus 1. Y plus 1, this is equal to plus 1 minus 1 equals 0, so we have m minus 1. So this is m minus 1, and when x equals 1, so when x equals 1, y equals to 1 minus 1 is equal to 0. So y equals to 0. When x equals to n, this is n minus 1. So y equals n minus 1, but n minus 1 is equal to m. So we can have m. So if you observe this one, this is equal, this one is equal to, same with this, our probability mass function with different variables. So they are similar. And as we take note, this summation from y equals to 0 to m, we know already that the sum of this probability is equal to 1 based on the properties of a probability distribution. So we can take this one is equal to 1. So we're left with mean is equal to np. So we have our mean. Let's now proceed on our derivation for our variance. So variance, this is equal to, we're gonna use the equation expectation of x squared minus the square of expectation of x. So in order to, we have this expectation of x, this is equal to np because mean is equal to expectation of x. What we need is this expectation of x squared. But before that, we can use the fact that expectation of x times x minus 1, this is equal to x. I will distribute x to x minus 1, so we have expectation of, this is x squared, minus x times negative 1 is negative, then expectation of x. So I have this expectation of x squared, and we already know this expectation of x, so I can have expectation of x squared is equal to expectation of x times x minus 1 plus expectation of x. Now, I need to derive this expectation of x times x minus 1 before proceeding with our expectation of x squared, then before proceeding again with our variance. So, I'll do it now. Expectation of x times x minus 1. This is equal to summation of x times x minus 1. Our probability mass function again. Let me see that. This is x, This is n chooses x times p raised to x and 1 minus p raised to n minus x. So we'll write it here. N chooses x times p raised to x, then 1 minus p. This is raised to n minus x. This is x from 0 until n. So in here, we will again take note that if x equals 0, this whole term is equal to 0. And if x equals 1, this whole term again will become 0 because 1 minus 1 equals 0. So we're left with x equals 2 until n. So we can just eliminate this one and make it 2 for our purpose on derivation of our variance. So again, similar to what I did in the mean, I will take again this x times x minus 1 times n chooses x. I will convert it to another term. So x times x minus 1 times n chooses x. This is equal to x times x minus 1 n factorial over n minus x factorial times x factorial. So again, similar to what I did before, I will remove some terms in here, n. So I can take n and n minus 1 but retain the n minus 2 factorial. Okay, so this one is again n minus x factorial, and I'll do that the same with x factorial. This is x times x minus 1 times x minus 2 factorial. So I can remove this x times x minus 1. I will cancel out this one and this one because they are same. Then I will simplify it again. So this is equal to n times n minus 1 times n minus 2 factorial over n minus x factorial times x minus 2 factorial. So please take note that n minus 2 minus x minus 2, this is equal to n minus x because negative 2 plus 2 equals 0. So this one can become n minus 2 minus x minus 2. So I can make it a combination. So this is n minus 2 chooses x minus 2 based on the formula of in combinatorial formula. So now I'm going to use this one instead of this one in here. So I can have expectation of x times x minus 1. This is equal to summation of, so this term become this term, n times n minus 1 times n minus 2 chooses x minus 2. Similar with our derivation mean, I want to divide this p raised to x into p raised to x minus 2 and p raised to 2 because negative 2, x minus 2 plus 2 equals to x. Then I will retain this 1 minus p raised to n minus x. Okay, so on our next step, so this is x equals to until n. So on our next step, I can move out n times n minus 1 and p raised to 2 because they are not dependent with x, so I can move it out now. N times n minus 1 times p raised to 2 summation of this is n minus 2 x minus 2 then p raised to x minus 2 1 minus p n minus x. Okay, x equals to until n. Now I will, similar with the mean, I will transform again the variables here into another variables to prove that these terms again is equal to 1. So let x minus 2 is equal to y and n minus 2 is equal to m. So this one is equal to n times n minus 1 p raised to 2 summation of. So n minus 2 is equal to m. So we have m. X minus 2 is y times p. This x minus 2 here is equal to y. And 1 minus p. So this n minus x. Remember that n is equal to, this is m plus 2. So n minus x. This is equal to m plus 2 minus x value is y plus 2. So this is y plus 2. This is equal to m minus y because 2 minus 2 equals 0. So this is m minus y. So with x equals 2, so y equals to 2 minus 2 equals 0. So this is y equals 0. And when x equals n, this is n minus 2. So y equals n minus 2, but n minus 2 equals to m. So we can put it here m. Again, similar to our style in the mean, this term here is similar to our probability mass function, and we take note that this summation is equal to 1. So we can take it here. This is equal to 1 based on the property of probability distribution. So this one is equal to 1. So what we're left with is n times n minus 1 times p squared. This is the expectation of x times x minus 1. So now we're ready to derive further. And okay, I'll bring back again the formulas. So variance, we know that variance, this is equal to what? Expectation of x squared minus square of expectation of x. But expectation of x squared is equal to this one, expectation of x times x minus 1 plus expectation of x. So we can put it here. This is equal to expectation of x times x minus 1 plus expectation of x minus so this is expectation of x minus square of expectation of x. So we have calculated already this term. This is equal to n times n minus 1 times p squared. This is n times n minus 1 times p squared. We have expectation of x. Okay, this is equal to np for our mean. This is np. So square of our mean, this is np squared. So let's again simplify these terms. So this is equal to, So this is n squared p squared minus n p squared plus np, this is np, minus n squared p squared. So we have similar terms here. This will become 0. And we're left with these terms. So it's equal to, we can get np here. So we can get np times negative p plus 1, or I can have np times 1 minus p. So this is our variance. For our moment generating function, so m sub x of t, this is equal to expectation of e to the tx, which is equal to summation of e to the tx times our probability mass function m chooses x times p raised to x times 1 minus p raised to n minus x. So from x equals 0 until n. So I cannot simplify it more. Maybe I can just collect similar x terms here. So this is equal to, I'll put the combinatorial here, and then this one, p e raised to t, this is x, so, and 1 minus p raised to n minus x from x equals 0 until n. So this is our moment generating function for a binomial distribution. So let's summarize our results. For the binomial distribution, the mean is equal to np, the variance is equal to, we have np times 1 minus p, and our moment generating function is equal to this term here.